Okay, let's dive into this. Welcome to today's Explainer, where we're going to tackle a subject that often trips up even the most focused learners, and that is grade 7 geometry. Now, why does it trip us up so often? Well, because it feels so fundamentally different from what you've been doing. You're shifting from just solving algebraic equations on a piece of paper to suddenly visualizing actual physical spaces and shapes. And that shift, that is exactly where the traps are hidden. If you've ever looked at a shape, known intuitively what you wanted to do with it, but then gotten completely lost in the numbers, you are definitely not alone. Today, we're doing a targeted misconception check. We're going to identify these traps, break them down, and give you the exact tools you need to bypass them. Here's our playbook for this explainer. 1. Spotting geometry traps. 2. Scale drawings and units. 3. Circumference versus area. 4. Unlocking angle relationships. And finally, number 5, the geometry self-check. Section 1. Spotting geometry traps, connecting visuals and numbers. Let's just normalize something right out of the gate. Our brains are incredibly good at recognizing visual patterns. But when we have to translate those visual shapes into abstract numbers and formulas, yeah, things can get pretty messy. We mix up the rules. But geometry is highly structural. It connects measurement, proportional reasoning, and visual structure all together. The secret? It is absolutely all in the details. The single biggest reason students make mistakes here isn't a lack of spatial logic. It's a failure to pay strict attention to dimensional units. Imagine you're building a birdhouse in woodshop, right? If you confuse a measurement of 10 centimeters for 10 inches, you're going to end up with a complete disaster. The pieces literally won't fit. And the exact same thing happens in math class. If you can keep your units straight, you can completely conquer 7th grade geometry. Section 2. Scale drawings and units. The reality check. So, we encounter scale drawings in the real world all the time. Think about maps on your phone or maybe architectural floor plans for a new house. But these everyday visual models can be incredibly deceiving if we don't apply the right mathematical translation. A scale drawing is basically reality shrunk down so it can fit onto a piece of paper or a screen. It uses a specific ratio to map the size of the drawing to the actual real-world size. For example, a map might use a scale where 1 inch equals 5 miles. This relies heavily on proportional relationships. The scale factor is basically the magic key you need to blow that image back up to full size. The trap here? Just measuring the visual model and totally forgetting to translate it back into reality using that key. Let's look at a real example of this. The number's 17.5 miles. Where does this come from? Well, imagine we measure the distance between two cities on a paper map, and our ruler says it's 3.5 inches. If our scale is 1 inch equals 5 miles, are we done? Absolutely not. No way. We can't just take that 3.5 inches and call it a day. We have to physically shift our minds from that plastic ruler on a desk to an actual car driving on a highway. We have to multiply those 3.5 map inches by our scale factor of 5 real-world miles. 3.5 times 5 gives us a real-world distance of 17.5 miles. Notice how the final unit completely shifted from inches on a page to miles out in the real world? And this brings us to a golden rule straight from our source material. Always ask what one unit in the drawing represents in reality. Failing to convert from your drawing units to your real-world units creates massive errors. I mean, picture telling your friend that the next town over is only 3.5 miles away, so you decide to just walk it. But you forgot to use the scale factor, and it's actually 17.5 miles away. You're going to be very tired and honestly very mad at geometry. That is the power and the danger of a scale factor. Section 3. Circumference versus area. The dimension dilemma. Now this is arguably the most classic mix-up in middle school math. It all boils down to confusing one-dimensional distance with two-dimensional space. On the left, we have circumference, which is the distance around a circle. The formula is pi times diameter. Think of circumference as the length of the wooden fence you need to build entirely around a circular yard. It's one-dimensional. It's a linear measurement, like regular centimeters. On the right side, we have area, which is the space inside the circle. The formula is pi times the radius squared. Think of area as the amount of grass seed you need to plant inside that yard. You obviously wouldn't buy grass seed to build a fence, right? This is two-dimensional space, measured in square units, like centimeters squared. You simply cannot treat linear distance and flat area as the same thing. So, what's the actual trap here? The trap is taking a one-dimensional scale factor, like doubling the side lengths of a shape, and applying it directly to a two-dimensional area without adjusting it. Students intuitively think, hey, if I make the sides 3 times as long, the area inside should just be 3 times as big, right? Well, actually, scratch that. Wrong. You absolutely cannot use 1D thinking in a 2D world.
Let's see how this trap springs on us in a real problem. Walk through this with me. Step 1. Start with a simple 2x2 square. Its area is 4 square units. Easy enough. Step 2. Let's apply a linear scale factor of 3 to the sides. So we multiply the sides by 3, making our new sides 2 times 3, which is 6. Step 3. Let's calculate the new area. 6 times 6 gives us 36. Now step 4. Look at the trap. Our original area was 4. Our new area is 36. The area did not scale by a factor of 3. It scaled by a factor of 9. Because you're scaling two dimensions, both the length and the width, the area scales by the scale factor squared. 3 squared is 9. This is exactly why paying attention to dimensions is totally non-negotiable.
Section 4. Unlocking angle relationships. Don't stop halfway. This one is a really unique hurdle because it's kind of like a vocabulary trap wrapped inside an algebra trap. First, we gotta lock in the vocabulary. Supplementary angles are two angles whose measures add up to exactly 180 degrees. Visually, when you put them side by side, they form a perfectly straight line. A really great memory trick for this is that supplementary starts with an S and they form a straight line. Contrast that with complementary angles. These are two angles whose measures add up to exactly 90 degrees, forming a sharp right corner. And here's your memory hook for this one. Complementary starts with a C. Just like corner, they make a 90-degree corner. Geometry relies heavily on knowing exactly what these specific terms mean, because the term itself tells you which mathematical constant to use for your equation, 180 or 90. But here's where things go off the rails. The trap is stopping right after you identify the relationship. A student will look at a straight line, say, aha, those are supplementary, S for straight line, and then just try to mental math the rest of the problem, completely skipping the algebra. When you're under pressure during a test, your brain can easily subtract incorrectly from 180. Setting up the written equation acts as a safety net. If you skip it, that's exactly where those frustrating careless calculation errors happen. So, the crucial point here is that you have to write out the equation. Let's walk through the proper playbook. Step 1. You see a straight line, so you identify the relationship as supplementary, meaning 180 degrees. Step 2. Write the equation. If one angle is given as 48 degrees, you write 48 plus x equals 180. Step 3, solve it algebraically using inverse operations. You want to isolate the variable x, right? So you subtract 48 from both sides of the equal sign. Step 4, your final answer is 132 degrees. By setting up the equation, you literally take the cognitive load off your working memory and let the algebra guarantee your accuracy. Bottom line, don't stop halfway.
Section 5. The geometry self-check. Game time.
All right, we've covered the traps. Let's do a rapid-fire scrimmage to really lock in these core concepts. Here's your scenario. Think back to our discussion on proportions and scale. What is the exact difference between similar figures and congruent figures? I'll give you just a few seconds to lock it in. 3, 2, 1. Okay, let's see how you did. Similar figures have the exact same shape, but they can be different sizes. This is where your scale drawings and proportional scale factors come in. Think of a picture on your phone that you pinch to zoom in on. Congruent figures, on the other hand, are mathematical twins. They have the exact same shape and the exact same size. No scaling required at all. If you slid congruent figures over each other, they would perfectly overlap without needing to zoom in or out. So, to beat the traps of 7th grade geometry, here's your ultimate checklist. Always check your dimensional units to know if you're working in 1D, 2D, or 3D space. Always finish your algebraic equations instead of relying on mental math. And always trust the formulas over your visual intuition. I'm going to leave you with this final thought. The next time you look at a blueprint, a map, or even a video game world, ask yourself, do you know the scale factor, or are you about to walk right into a geometry trap? Keep your units straight, and you can map out literally anything. Thanks so much for learning with me today, and I'll catch you on the next explainer.